Hello, this is Dr. Hassan Abdullah with the course Deep Reinforcement Learning, and the topic which we are covering in this video is Basic Gradient Descent. And this topic is the third topic in the list of topics of the course. And these topic uh, divided into three subtopics: 3A, 3B, and 3C. So basically, there is a progressive increase in the difficulty of the content. So we move ahead with the topic, the lecture 3B, using the specialized learning management system easymcq.com/goget. So we have the list of topics on the screen, and we are at the third topic, which is the basic gradient descent, which consists of 15 Q&A. Now these questions and answers are basically concepts which are further divided as can be seen. So where here we have the detailed list of the Q&A which are covered in this video, and we are at the second one, which is 3B, highlighted in green color. Now without further ado, we move on towards those concepts and discuss them in details. So we are at lecture 3B, which is deep enforcement learning. Topic is gradient optimization, basic gradient optimization. And we start with the first Q&A, which is what are the nuances and challenges of gradient descent optimization. Nuances means basically finer details or finer things which can have an impact. So what we are looking at basically are these have an impact. These five have an impact, and I will also share with you two diagrams also, which will clarify. So before actually we start working on them, let me show you those diagrams. So this is all the explanation which you will be reading. So we have this is the weight function, and this is something which is this is the weight basically on the x-axis, and this is the loss basically, which is function of the weight. So what it is telling us that, and this is that kind of a smooth ball region for the search space, and this is for the sake of simplicity of understanding, because in real life we won't be finding this kind of relationships, right? So anyway, so we would like to reach this the local minima. So we are looking at the step size. So if the step size is too small, the convergence will be there, right? uh, it will not overshoot, but it is going to be very slow. That is the step size. And if the step size is too large, it can, as a matter of fact, overshoot, right? So the step size is too large. So from there, go all the way to there, and then have to come back again. So of course, this will take less time, right? But in terms of effort, it is just kind of oscillating. Number one. Number two is that this figure this is convex, as I mentioned before also. Why it's convex? Because if you join any 2 points on the parameter, the line will remain within this figure, so that's why it's convex. Okay, in real life, as we'll see in this question, as a matter of fact, this search space is not convex. It's not convex, and it becomes a problem. Same is true for this one also. This Yeah, this one is well, when we come to this, I'll discuss with you. All right. So we are at these points for learning rate tuning. So what is meant by learning rate tuning? Learning rate tuning means that basically what we are looking at is how much the model updates during the training. So if the rate is very high, it may cause divergence, which I've shown you. And if the rate is low, then the convergence is very slow, which I have shown you. So the thing is that we are looking for the right balance, and that right balance is crucial, right? And because it requires schedules and it requires something called as adaptive optimizers, right, for effective and stable learning. So this I've shown you. So you understand, of course. Then we have data sampling methods. So what are data sampling methods? Gradient updates, right? And this gradient updates can be use full data sets, or it can use single examples, or it can be mini batch, which we already covered. So whatever the method which we use, one thing is clear, that it will have an impact on the speed, it will have an impact on the memory requirements, and then will be a convergence behavior also, which we have seen. So what we have already discussed in a previous Q&A, that mini batch is the best of both worlds. It balances the efficiency, and it is and the stability, right? But the question is that what should be the optimal batch size? Okay, and of course, what should be the sampling strategy? So that has an impact. So let's move on. Convergence issues. Convergence issues basically, as we have discussed before also, but now we are in some more detail, that when the gradient descent reaches a saddle point, or it gets trapped in a local minima, right? Then it can stall. So which is, and of course, if it's a plateau, they this is which is called as they have they face vanishing, deep net face vanishing issue, and of course this is something called as exploding gradients also, and it has a long term effect across all the layers if it happens in the early layers. So what will be the outcome? The outcome of these issues is slow, okay, and slow learning, or it will prevent learning. And of course, that will require some careful initialization, normalization of the layers, or using robust optimizers. So what we were trying to avoid the human in the loop, so we end up putting the human in the loop with all the issues. Okay, so loss surface complexity, which we'll cover in the next Q&A. So basically, the loss surface, right? That surface is basically a 3D space. So what we have been looking at the 2D. So this loss surface can be highly non-convex. Now you know what is convex, and it can contain many local minima. Minima. So I'll show you more about it, talk more about it. And it can also have saddle points, and it can also have flat regions. So what happens is that our gradient descent kind of gets stuck, okay, and the optimization becomes difficult, and it becomes unpredictable. Why? Because of these issues. So we have something more which we'll be discussing soon, which is called as momentum based methods. So by using those momentum based methods, and good weight initialization, and some other techniques, right, like residual connections, so we can kind of handle or manage the surface complexity. Okay, so this will become clear in the next Q&A. And then are the scalability concerns. Now one thing should be clear to you, that for large data sets, right, and if that loss surface is very large in terms of number of variables, remember that it can be multidimensional. So for the sake of understanding, we are keeping it only 2D and 3D, but it can be multidimensional. So for large models, multiple dimensions, large data sets, this gradient computation can be very expensive, right? And it can require a lot of memory also. So it means that it is going to be memory intensive, obviously. So those methods will require full batch, they are impractical. Therefore, the obvious solution is parallelization, if it can be achieved, or it can be distributed training, or there can be other techniques which are memory efficient. Now, when you parallelize, okay, and you distributed training, then there are issues of synchronization. Why? Because unless everything is available, how can you move ahead? And there can be hardware constraints or the communication overhead or the bandwidth overhead, and of course that will affect the scalability, and of course that will affect the overall efficiency also. So we see that we need to take into consideration all of these things. All right. And whosoever can do this, they'll be, of course, will be the winners. All right. So this is the explanation of what I've briefly described, and here are the references if you're interested in knowing more. So this is interesting question. Now, for this is the loss surface. This is the loss surface complexity. So this is the loss surface, okay? And this loss surface is represented by this equation. And the question is, draw the 2D and 3D search space for the following function and also describe this. This is very interesting and challenging. So first of all, it's a non-convex landscape. How do I know that? Because of this term. This is this term and this term showing that this is non-convex, because it will have its own growth rate much higher than this one, right? So this is for sure not, this is not a convex, for sure, no doubt about it. So draw this and also describe. All right. So okay. So this is a non-convex landscape. Then these terms have their own interaction, their own impact, and then there are saddle regions also. Saddle regions, one side is increasing, other side is decreasing, and then there are other dynamics also. So let's look at them briefly. So what I'll do is this equation basically I divide into three parts. So let me show you those three parts. Yeah, there are the three parts. This is the green part, this is the blue part, this is the purple part. So this basically, this we need to visualize this, right? So and then we need to adjust the model parameters also, right? So this function is going to generate a non-convex landscape. So what does it mean, this is non-convex? It means that the pictures which we have been looking at, the surfaces which were like a smooth curved like a bowl, it's not going to be the case over here, because this green term, right, that adds a steep and asymmetric curvature. Green term, this is the basically this is the green term. All right, and the blue term are this will introduce like twists and slopes. This will reduce, and this will just like take it a step above 3 units. So what's the end result? The end result is a complex terrain, and that complex terrain is what you can call a hallmark of deep learning loss landscapes, especially in high dimensions. We are just looking at two dimensions, x1 and x2, but there can be many more dimensions, right? So I was talking about this basically. So so what's going to happen? This basically this landscape is going to trap the gradient descent, okay, in a local minimum. or it gets trapped at saddle points. So what's will the end result will be optimization will become more challenging, and it will be less predictable. You won't know what's going to happen. Okay, let me show you this its picture also, so that things become clear. Yes, this is it. So this is the 2D view. This is the 2D view of this function, and this is the 3D view. And as you can see that this is the global minima, this is the local minima, and definitely this is not convex, because if you connect these 2 points get they do not remain within the region. So this is definitely not a convex figure, and that definitely has this is the global minima, this is the minima, this is the local minima, and it is not a smooth bowl kind of a structure which we had seen before this Q&A. Okay. All right. So let's go back to the bullets. So this is definitely challenging, right? Then are the interaction terms. So these are the interaction terms, right? Okay, they basically warp the loss surface, right? So they kind of influence each other. They complicate the path and make the gradient direction sensitive to parameter combinations. If it was there only, then it would have been a smooth one, but that adds to it. This would have had a slope higher than a quadratic because its power is 4, but this adds complexity to it, right? And this makes it difficult for that blind man approach to reach the local get out of the local minima or to go to the global minima. So then there are saddle regions also. So these saddle regions basically uh, gradients vanish, okay, in one direction, right, but not in another direction. So these flat regions, you remember, are common in high dimensional, okay, spaces, and then the optimizer is going to have a hard time. So either they will stall, okay, to not work, or they will take small steps to be careful, and even when the descent direction exists. So it's just time consuming, resource consuming. Then what are the gradient challenges? The details are down there. Gradient challenges uh, are are caused by the quadratic term, and this term can lead to vanishing or exploding gradients, and it depends upon where you are on that lost surface. So these things are going to relate to and affect the training of the deep networks, especially when there are layers are deep or they are not properly initialized. And this is going to cause problem during back propagation, which we have already discussed in the lecture 3A. So finally, we end with the optimization dynamics. So what are optimization dynamics? So optimization dynamics basically this is the this is the trajectory of the optimization on the loss function surface. And of course, as we can see right now, let's go to that picture. So the optimization trajectory is how we move on this, right? Say we move like this, or I think I picked the wrong object. So we move like this or go like this, and this is the optimization trajectory, right? So this optimization trajectory basically it zigzags, okay, and it will be highly, and we can see it's not linear, and it will be slow on plateaus because of the zero gradient, and it may overshoot also. So there's to the optimizer is having a hard time, right, and trying to reach a good minimum, right. So it depends upon the learning rates, it depends upon the algorithm used, it depends upon the training of the algorithm and so on. So this is a challenge, right? This is a challenge. Okay. So adding more to the challenge is a more interesting and challenging question over here. That this is the what is this? Now you should know this. This is your loss surface. And this loss surface basically uh it's quadratic, that's for sure. It's quadratic. So the question is like for that learning rate. So we discussed before that the learning rate can be h of k and can be alpha also. So we had that, if you recall, it was w uh, and associated with alpha value. So h of k is basically depending upon the iteration, and this is kind of fixed, right? So this is fixed, alpha 0.37 and alpha 0.39. So how would the gradient descent takes place? Now over here there was no constraint. Now we put a constraint about the value of alpha. So basically this is defining a convex surface. How? Because it's quadratic. It is quadratic. Now it's entirely quadratic. So there is no other function, right, of cubic nature that could have caused it to become non-convex. So this looks like a elliptical bowl, okay, and of course there is a single minima. But the thing is that how the gradient descent takes place, it depends upon the learning rate. It depends upon the learning rate, okay. Depends upon the learning rate, okay, which controls the size of the step. So when alpha is, let me open the bullets, okay. So we have a stable descent and we have something called as the near instability. This is stable, this is near instability. So this instable descent where alpha is 0.37, the descent progresses, of course, steadily towards the global minimum. The learning rate is small within a safe range. So what's going to happen? It's going to be consistent, stable updates without overshooting. And it will take time, but the algorithm will efficiently reduce the function's value at each step, and it will ultimately converge reliably, okay, for most of the initial points from where it started, right? So the starting point can be different, which we have already discussed. I'll show the picture also. And this when alpha is 0.39, then it's near instability. Why? Because gradient descent operates good near the stability threshold. Now, if now we are discussing it without solving any equations, so this will result into larger steps, and it may cause oscillations, which I've shown you before, going from one end of the parameter of the space of the 2D space to another, and this process becomes more sensitive, right? As the starting value may require, depending upon the starting value, it will behave erratically also. So let's look at the picture or the diagram. So this is alpha 0.37, and it is like a smooth ball, okay. This is the 2D, and we can see that it started and then it ended and it is kind of basically you start from there and you move like this and go and reach the global minima. And over here you can see that starting point is almost the same, but because of the very large value of alpha, they it just overshoots. It just overshoots. So this is diverging, this is converging. A big difference over here. Okay, so you have to be careful about it. So now we have a more challenging question. The question is that how to choose the learning rate. How to choose this learning rate, right? And what are the three values? The reason being that the three values which you are looking at, small alpha, large alpha, and fixed alpha, because choosing the value of h of k is critical. Why? Because it affects the efficiency and effectiveness of the optimization process, whatever that value may be. So this learning rate basically controls how big a step is going to be, and how much, how many iterations will be there, and how the loss function would be minimized. So there are three options: small alpha, large alpha, and of course fixed alpha. So what is in small alpha? The small alpha, which we discussed before also, it ensures stable and precise convergence, but it is slow. And it converges instead of diverging, that we've seen twice, and it prevents overshooting the minimum. But of course, it can get stuck at the saddle points or at the plateaus. Okay, and of course, this can be used later at for fine tuning purposes also. So it has some issues also. Let me show you the diagram so that linking could be better. I think it should be better now. So we see that we have small alpha, right? And it converges, but it is slow. And when the alpha is large, it the convergence is very fast, and it can get out of the local minima because it jumps like this, and this cannot get stuck. Or you can say that it's less likely to get stuck. Okay, but this is not stable. Okay, because it overshoots and it can diverge entirely. So it is good for early training, right? But then you have to reduce it for stability. So this is early training, going from there to big jumps, and then small jumps. So this is just like simulated annealing, which you may or may not have studied. So it is just like, say for example, you are traveling between cities, two cities. So so first you are driving very fast, and you have fewer turns to make, big motions, and when you enter the city, then you are driving slow, and you are making a lot of turns because you don't want to miss your destination. So we have small alpha, we have large alpha, and then we fix alpha. So what is fixed alpha? Keeps alpha constant throughout the training. It is simple, right? But it is inflexible. So if it's not properly tuned, it may cause obviously slow learning, as in small alpha, or it may cause instability. So what is done is something called as decay schedules or adaptive methods which change themselves for better performance, right? So over here the alpha is small, over here the alpha is fixed, right? Okay, so let's move on to the last Q&A. So what are the issues of gradient descent optimization as shown in this figure? Which figure? This figure. So if you look carefully over here, so if we are looking at minimization, so we start with the global minima, and we have this global minima, and then this minima B, is a local minima. This is not global. And this minima over here, C, that is also not global. So we start from the global minima, and as we move in this direction or change the weights, there are always chances of getting stuck in those local minimas. So what we would like to do ideally, okay, let's look at over here. So ideally, we would like to, of course, if we arrive at A, which is the global minima, is wonderful, but that may not be possible because there's a local minima B, which is almost as good as the global minima. So that could be an acceptable halting point because this is memoryless operations. But this local minima C is very poor, as we can see, and should be avoided. So what options do we have, and how do we go about uh, uh, preventing getting stuck? Initialization sensitivity. So as you must have been noticed by now or understood, the gradient descent outcomes are heavily dependent upon the starting point, right or not? So where you start, it depends where you will end up. So if the starting point is beyond A, okay, the optimizer may never reach A and settle at B or C, and the result will be suboptimal, right? So what I am saying is that you do a lot of movement here. So if we start from here, for example, then unlikely to reach here. So either settle at B or settle at C. A is gone. Okay, then is the what was the bullet before? Next bullet was local trap risk. So what is local trap risk? So once the gradient descent reaches B or it reaches C, it will not be able to escape. Okay, because if it moves in this direction, you have to come back. This direction you have to come back. This direction you have to come back and come back. So we'll get trapped in the local minima. No way getting out of it. So what is the solution? Random restarts. So starting point changing because the optimizer gets stuck. And so why? Because it has failed to reach the global minimum. Okay. What is the next? Learning rate balance. Learning rate balance means that uh, whether it should be the rate should be alpha value we're talking about. What should be the value? Small rate, high rate, we have already discussed that. Then the vanishing gradients. Because if we have this is vanishing gradients. So we don't have vanishing gradients. Here we have a chance of a vanishing gradient over here. Here we also have a chance of a vanishing gradient. So because the slope is zero, slow learning, and it is going to have the optimizer from moving forward towards the global minima A. So if the weight increases and gradients vanish, the model will will get stuck over there. It's not gonna come out of it. And finally is the non-convex length. This is non-convex because if you connect these 2 points from here to here, it gets out of this region. So functions are non-convex and there are multiple minimas and decreasing quality. This is the best quality, then this is worst. Very similar, but this is the worst one. So get stuck. Misleads the gradient descent into local dips. There is no global information. So the optimizer thinks that all of them are equal, difficult to understand, and of course, then it can get stuck at B or C. So we see that this, which seemed to be a kind of a easy loss surface in 2D, it turns out to be very problematic. So we have to take V means the optimizer has to take all of this into consideration. So that's all for this topic.